And welcome my wonderful honor students to a very special video for you today. We're going to be talking about projectiles with angles. And this is all about the concepts and a bit of math, what happens when you fire something at an angle. We're going to look at a very special situation involving those angles, and maybe even apply it to your trig class, or any other math class you had recently. So last time we discussed projectiles that are only launched horizontally, like you see here. We know for a fact it only starts off with horizontal velocity, so there's no vertical motion at first. And what we said from that is that the y velocity at first is 0. But right after that first moment, it has y velocity and it keeps getting more and more negative, that is faster downward because of gravity. Let's look at a more complicated situation. So here's a situation where you shoot something off at an angle and it ends back at the same height, and it ended up some distance x away. This little arrow right here shows that it started off at that initial velocity, but it's going to change because gravity's pulling it down. Here's another situation. You fire up at some angle and it ends not at the same height. It ends above where it started. And then finally, you shoot something off and it ends below where it starts. All three cases involve angles. And all three involve this arc because it's at an angle. So even though it ends down here, it still goes up for a little bit. Still goes up for a little bit, comes down. Goes up, and eventually comes back down. So therefore, at the first moment, it has an initial velocity in the x and an initial velocity in the y. What angle will those two velocities be the same? And you probably said it, 45 degrees, because the cosine and sine of 45 degrees are equal to each other. And like always, we're going to use sine and cosine to find the x and y velocities at this starting point. Let's look what I mean. Here's something that started and ended at the same height and is fired at an angle. The blue arrows represent how fast it's going horizontally. The red represents how fast it's going vertically. And they're looking at 7 time points. So notice what's happening here. The forward or x velocity stays the same because gravity don't pull it left or right. So it's not accelerating, it's 0, but the velocity remains constant in the x. But the y velocity is different because it has acceleration, which is gravity. As it's going up, the y velocity gets smaller and smaller because it's getting pulled down because of gravity, till at the top point of it, there is no up and down motion. The y velocity is 0. And then as it's on the way down, the y velocity gets more and more negative because it's getting faster downwards. Notice, at any height, like this height right here above the ground, at the same height on the other side, it's the exact same blue arrow size, and it's an equal and opposite red arrow. Here and here, same, here and here. The only point it doesn't have it is the top, because there is no other height that you go to the top. There's nothing else that's paired with it. It's not symmetrical at that point. And that's why the velocities here is 0. So by combining x and y and overall, we learn that at any height, the same height on the other side of its parabolic arc will have the exact same velocity. X, y, and overall. So if you fire a gun into the air, even at an angle or straight up or whatever, when it comes back down to the exact same height, i.e. the height you started at, even though it may be very far away, it has the same velocity left the gun at, which means it's still deadly as heck. Here is an awesome looking picture. This is showing the same initial velocity fired at all these different arcs. What's really cool here is that you might see the 75-degree one takes a lot of time. The 15-degree one takes very little time, but they both hit the same place. Same with the 30 and the 60. We just learned that at the same velocity, complementary angles hit at the exact same distance in the x when the y distance is 0. So if you're a little cannon right here, and you fire a shot at 60 degrees and a shot at 30 degrees, they will hit at the exact same distance away, but not the same time. So if you're really smart and there's an enemy there, you fire 2 shots. You fire your first shot at 60 degrees, and then when it's a little bit away, from about to hit, you fire the second shot at 30 degrees. And if you time it just right, apparently 0.73 seconds apart, they will both hit at the same time, and you have what's called time on target, which is an artillery term for firing all your guns and firing multiple shots. They all hit at the same time, saturating the target. And we just learned that they're all going to hit the same velocity. So it's not like you're losing impact because you fired higher. You're getting more time in the air to hit compared to the 30-degree one, but hitting the same velocity. Here's an example for you to copy down after you pause this. It's going to have two parts, a math part and a conceptual part. I'll wait. I'm done waiting. A cannon fires a shot at 120 meters per second at a 30-degree angle above the horizontal. That's our situation. Part 1, the math part, is how high is it and how far horizontally is it from the start after 2 seconds in the air? So we're looking at the shot right then. How high is it? High means y, and it also means distance. We're trying to find the distance in the y here, or really the displacement. How far is, again, a displacement horizontally, x. We're trying to find the x and y displacement after 2 seconds. But the first thing we should do here is, because you see the word angle, we're going to find the x and y parts of this overall initial velocity. So to do that, let's draw a picture of the overall initial velocity. There it is. Let us then draw on the x and y parts, label them positive, positive, opposite, and adjacent, and we could use our sine and cosine tools to find those x and y initial velocities. Because when we analyze this stuff, we have to look into x and y differences, because gravity does not pull at a weird-ass angle like this. Gravity only pulls down, which is in the y. Using my two terms, cosine is adjacent over hypotenuse, sine is opposite over hypotenuse, I can now use the hypotenuse, which is 120 meters per second, which is the initial velocity, and solve it. You can see how I plugged in the angles here, and then the adjacents and the opposites, and the hypotenuse. And you can see how I solve for the x and y. Remember, these represent the initial velocity. If you're ever unsure, take a look at the number you put in the hypotenuse, the one at the angle, and that's the starting velocity of it. Now, if you say it's also the final velocity, you're wrong. It'll be the final velocity if it was ending at the same height it started with. We don't know that, though. We only know it's 2 seconds in the air, so we can't assume that. So what we're going to do now is we're going to make number lines and then tables from that. We're going to do it again for x and y. Here's my x number line. It starts off at some point, ends forward. It starts off with a velocity of 103.9 at 0 seconds. It has no acceleration because gravity don't pull left or right. And at the end for us is after 2 seconds, trying to find the d. For the y, it starts off here and it goes up. The initial velocity is not 0 because if initial velocity was 0 on y, it could not go up. And we found it to be 60 anyway, so we know that's good. That's at 0 seconds. After 2 seconds, trying to find how high up that is, and we know there's a negative 9.8 meters per second squared of acceleration because it's in the air. So we're going to make a table from this. I just took these numbers and these numbers from the table here. I'm trying to find d. So we could easily choose the correct equation, and we're going to solve for it. I chose this equation for x in blue. I'm putting the numbers here. Notice the acceleration is 0 in x. So I could solve for it. I got 207.8 meters. That's how far forward it's going to be after 2 seconds. Then I use the same thing for y and plug it in numbers. All the variables have numbers. There's no zeros here. I get 100.4 meters. That's how far up it's going. I'm sorry, whoa, that's how far up it was after 2 seconds. So after 2 seconds, it's more far forward than it is far up, which makes sense for 2 reasons. Number one, at 30 degrees, it's mostly horizontal, so you're going to have a lot more forward motion than up motion. And number two, the positive displacement means it's still above where it started, but it can't be up there forever because gravity's going to pull it down. Cool. Now let's do part 2. I'll pause while you write this down. Whew, that's a lot of questions. When the shot reaches the max height, what will the x velocity be? X acceleration, y velocity, overall velocity, time shot in the air. Seems like a lot of math here, but really, 5 of these 6 can be answered with no math. Here's what I mean. New number lines. Starts out with a velocity 103.4, acceleration 0. At the max height, we don't know how far forward it was. In the y, we know this velocity is 0, gravity's at 9.8. And we know that at the max height, it's not moving up or down for that one point. So the velocity is 0 at that point. That's the final velocity. So the x velocity, well, if it's no acceleration, we know the acceleration at x is 0 at the top. Nothing special there. And since there's no acceleration, the velocity of 103.4, or 9, I'm sorry, is going to be the same for every point while it's in the air. Remember that earlier picture we wrote where the blue arrows don't change. So at the top, the starting point, 2 seconds in, 3 seconds, 4 seconds in, I don't care what, the x velocity will be 103.9, always, because it's 0. So there we go, we got 2 of the 6 done without any math. But we're still smart like that, because we know in the y velocity, it's 0. Because at the top of the arc, there's no vertical motion. And even though it's not moving, at every point in its arc vertically, the acceleration is negative 9.8. Cool, we got 4 of the 6 questions done with no math. The 5th question, what's the overall velocity? Could have a math answer, we don't need it. At the top, it only has x velocity, not y. So the overall velocity is the x velocity, 103.9. As proof, to find the overall from x and y, we have to use the Pythagorean theorem. So at the top, the overall velocity, c squared, equals a squared plus b squared, where a is the x velocity at that point, and b is the y velocity at that point. But at that point, the y velocity is 0. The x velocity is always that same number. So if you solve for this, you get the overall velocity is just the x velocity. Okay, that makes sense. Now for the time it's shot in the air, we do actually have to use math. We know the final velocity is 0 in the y. The initial velocity is 60. The acceleration is negative 9.8. We could solve for time, we get 6.12 seconds. It's not the math that's hard. It's simply knowing what to use, and more importantly, what can we assume based on the situation. And that's why you guys are going to be awesome. If you have any questions, please ask me in class. It was a pleasure to teach you today. Goodbye.